thank you, Christina, for coming.
Thank you very much, and thank you to you and to Duncan for inviting me to speak in the seminar. Of course, I would have loved to be in Montreal, but that's not possible, so I'm very happy that I could do this instead. And I also want to thank Charles, who's in the audience, because he's my collaborator and very much a big part of this talk, so as you will see. So I'm going to talk about Sasaki-Einstein metrics and the iterated join, or rather motivate the iterated join via Sasaki-Einstein metrics. So it's sort of an idea of, yeah, well, it's almost in the name. Take the Sasaki join, and then if you get a good metric, and if it's quasi-regular, try and do it again. Do the join again and again, and sort of in a non-trivial way, get some new examples. So we're going to have to do some foundational work first in order to get it started, and I will talk a little bit about an example and how difficulties arise when you really have to do the iteration forever. So let's get started. So I'm just going to have one slide reminding us of the Calabi-Einstein metrics, because they are lurking in the basement of Sasaki-Einstein metrics. So here we're going to let a n be a smooth, compact manifold, but we'll allow it to be an orbifold of real dimension to d, subscript n, if there's others in play. And by Kähler structure, we mean a integrable, almost complex tensor here, a Riemannian metric that's a Hermitian with respect to J, the corresponding 2 form omega that's closed, that's the Kähler form. And because it's a Kähler form, and because it's closed, it has a second cohomology class, which we will call the Kähler class. And if we fix a J, then all the classes in the second cohomology group that has a Kähler form as a representative are called the Kähler cone, that set. All right. Now if we take the Riemannian Ricci tensor with respect to G and bring in the complex tensor, we get a 2 form called the Ricci form. And the miracle of Kähler geometry is that the first Chern class with respect to the complex structure is actually given by the Kähler forms class, more or less, up to 2 pi. And then Kähler-Einstein condition is, of course, that G is Einstein, but if we write it in terms of the Ricci form and the Kähler form instead, it means that the Ricci form is a constant times omega. And that, of course, immediately implies that if you have a Kähler-Einstein metric, the first Chern class has to have a sign or maybe be null. And also just sort of, by the way, Kähler-Einstein is a stronger thing than constant scalar curvature. So Kähler-Einstein implies constant scalar curvature. And in fact, that constant lambda is related to the scalar curvature. And this is not a talk about Kähler-Einstein metrics, so I'm not going to go into existence and all that about those. But this is just the basic definitions. Okay. And now let's bring in Sasakian geometry into this. So the slogan is that it's the odd dimensional sibling of Kähler geometry. So what happens is you take a odd dimensionable, and I'm going to assume compact smooth manifold. And on that, you have a psi, that's a V vector field. You have an eta, that's a contact form. You have this, which is a CR structure on the corresponding contact bundle. And you have a Riemannian metric. And whoops, what is happening? My mouse is not working. Whoops. Okay, I have to use my keyboard. Where All right, so this is just what I just said, but a little slower. Eta is a contact one form defining a sub-bundle. The kernel of that is the contact bundle in the tangent bundle. Psi is the Reed vector field of eta, and here in parentheses are the conditions for being this Reed vector field, and that is unique. And phi is an endomorphism field which annihilates psi and satisfies that restricted to the contact bundle, it's a complex structure. And d eta then becomes J invariant. And then the Riemannian metric is related to eta and phi in the way that, see here. Let me see if my mouse works again. Nope, does not. All right, so psi is a killing vector field of G, so it the Lie derivative of G with respect to psi is 0, and it generates a one-dimensional foliation of M, whose transverse structure is scalar, so it's a scalar foliation. Another way of seeing it is that you can form a, and this recycling the same name, scalar cone over M, so beef up the dimension by 1. Then there's also a scalar structure that's related to the eta and phi as well. So that's just two ways of seeing it. So standard model would be to think of S3 lying in C2, hovering over CP1. All right. So apropos of that, the corresponding scalar foliations sort of fall into 3 different categories. If psi is regular, that means that psi generates a free S1 action and the quotient is a honest, smooth, compact scalar manifold, of course with a scalar cohomology class in the regular cohomology group integer, because it's also a S1 bundle. The Sasaki manifold is a S1 bundle over the scalar manifold. If it's quasi-regular, it's only a locally free action, and there the quotient gives us an orbifold. So we say quasi-regular for that. And in that case, the orbifold scalar cohomology class lies in the orbifold second cohomology group, which you'll see this later, I sometimes think of as sitting in the rational cohomology group. If it's not regular or quasi-regular, it's irregular, and that's actually most of them. But this talk will not be about the irregular structures, so I'm not gonna mention them anymore. We'll ignore those. Also, just to bring it back to this scalar geometry miracle, the orbifold Chern class of the quotient, in case of the quasi-regular case, is pulling back to the basic first Chern class of the foliation, which is the class, the transverse class of the transverse rigiform. So, all right, and then just a reminder that Sasaki structures comes in rays. So if you have a Sasaki structure, you can quote unquote rescale it. You're not really rescaling it on the quotient, you are, but not along the Reed direction this way. So anytime you have a Sasaki structure, you have many in a ray. And a lot of the nice geometric properties are sort of preserved in the whole ray. All right. And because it will be sort of a fine print later, I'll talk about deforming the Sasaki structure within its isotopy class. So if you take your contact form, and to that you add dc of phi, where phi is a basic function. So in general, if you have a basic form, it means that the exterior product with psi is 0 and the Lie derivative with respect to psi of phi is 0. But that corresponds to deforming the transverse scalar form like this in its basic scalar class. And so if we have a regular or quasi-regular class, you are deforming within the scalar class on the quotient, the orbifold, or manifold if you're lucky. So when we say up to isotopy, we mean that we might have changed our Sasaki structure with respect to that. Okay. Another way that we can deform a Sasaki structure is within the Sasaki cone. So just quickly talking about that, if you pick a maximal torus in the Sasaki automorphism group, then the unreduced Sasaki cone is the collection of elements in the corresponding Lie algebra, where eta on the corresponding vector field is positive. That can then give us a new Sasaki structure with the same underlying CR structure. Okay. All right. So Sasaki-Einstein metrics are metrics that are both Sasaki and Einstein, so that's the definition. But to get the underlying or transverse scalar structure with us as well, let's go through this a little slower. So the Ricci tensor of G behaves in sort of interesting way. So on X and the read vector field, it's 2n eta X. Any other vector field, and if you take sections of the contact bundle, it's looking like this. So RT stands for the transverse part of the Ricci tensor. All right. The scalar curvature behaves a little bit sort of nicer, a little more straightforward. So the scalar curvature is the transverse scalar curvature minus 2n. All right. If the transverse scalar structure is scalar Einstein, then we will say that the Sasaki metric is eta Einstein. So it's not necessarily Einstein, but we say it's eta Einstein. And a Sasaki structure is eta Einstein if and only if its entire ray is eta Einstein. If you have eta Einstein and the transverse scalar curvature is positive, then exactly one of the Sasaki structures in the eta Einstein ray is actually Sasaki-Einstein. So you can get to sort of the right scale going there. All right. And if a Sasaki structure is Sasaki-Einstein, then one can calculate that the first Chern class of the contact bundle has to be a torsion class. So for example, and often for practical purposes, if we let it vanish, then it's okay, right? So it's not, it's a necessary condition that it's a torsion class, and you will go a little bit beyond the necessary condition if you make it vanish. All right. And just to finish the story about constant scalar curvature, Sasaki structure has constant scalar curvature if and only if the transverse scalar structure has constant scalar curvature. So in that case, the whole ray has constant scalar curvature. Okay. All right. Okay, so I'm going to use S1 orbibundles a little bit. So I will sort of briefly present them in the way we think about them. And I'm following very much the philosophy of Charles and Galicki's book. So Boyer and Galicki's book, Sasakian Geometry. So the way we're gonna think of orbifold here is that we have a pair, so a projective algebraic variety, together with a sum of irreducible branch divisors, delta n. And so we take all the the wild divisors and we introduce orbifold structure on at least some of them, if mj is not one. And these singularities, they will all be finite cyclic quotient singularities. And then we kind of sort of view that as something that we add to the structure of n. So, and in chapter 4 of the book by Boyer and Galicki, all that is laid out. So it turns out that one can treat orbifolds this way. Okay. Oops. And then by also theorem 4315 in this book, we have that the isomorphism classes of S1 orbifolds, orbibundles M over this base are uniquely determined by the orbifold first Chern class. So, and that's a class that, of course, it's sitting in the second orbifold cohomology group, but we can think of it as sitting in the rational cohomology group, as long as we're a little mindful of what the denominator, so to speak, is allowed to be. That has to do with the order of the orbifold. Okay. All right, and when such a bundle has a Sasaki structure, then that goes hand in hand with that first Chern class is actually an orbifold Kähler class. So there's a Kähler structure along with that. All right. So I'm now going to talk about the generalized orbifold Calabi construction, and that comes from a lot of people's work, and in particular joint work that I've done with Apostolov, Calderbang, and Gordishan. So we are just generalizing this tiny bit, and we're not the only ones who thought about that generalization. So and we're just sort of doing as much as we need. So here we go. So I just want to acknowledge that there's some history behind all this, very, very large history. And the phrase generalized Calabi construction, I believe, was appearing in Apostolov, Calderbang, and Gordishan's my paper first, that phrase, you know. And here what we do is we make a modest generalization allowing for the base space to be a normal projective algebraic variety with a cyclic orbifold singularities. But other than that, we're going to stay in the admissible niche of this construction. And in that form, so in the form that we call admissible in the papers, you know, joined with Apostolov, Calderbang, and Gordishan, there's definitely credit due to a lot of people, including Calabi, Guan, Wang, Koiso, Lebrun, Peterson, Poon, Sakana, Singer, Semanga, and others. So this is well-established constructions that, you know, have several decades of history. Okay. So I'm not going to go into the details of this, but just enough so we can see what the objects are. So the ingredients that we're throwing into this is we need a base. And so as I said here, the base will be a cyclic Kähler orbifold. And I'm going to assume I have a metric on that, that for practical purposes, I'm going to call G base. And that scalar form is 2 pi times omega n, because I want the class of omega n to be a primitive orbifold Kähler class. So I have to tuck this 2 pi away somewhere. And what I mean by primitive orbifold Kähler class is that it's really a primitive integer class that is sitting over, you know, an integer that is the order of the orbifold. And so the order of the orbifolds depends on the choices of the ramification indices, these lowercase m's that were introduced before. So it's the least common multiple of all of them, something like that. Okay. And then we have a fiber. And this is this has been done several times by many, you know, that the fiber doesn't have to be CP1, it could be a weighted projective line instead. So here it is, I'm going to call it CP1M, and then M is a pair of integers that are not necessarily co-prime, but if I take out the greatest common divisor, then I'll introduce these letters V0 and V infinity. So, all right, so we can think of this as weighted projective line over a cyclic group like that. All right. And then we form a principal S1 orbit bundle over this base with a principal connection that is coming from the Kähler form, but I'm introducing an integer here, n, as well. That can't be 0, but otherwise it can be positive or negative. Okay, and then we're assuming that this S1 orbifold bundle is so that the S1 acts on our weighted projective line up here. All right, and for also sort of practical purpose and not have redundancy, we're assuming that the greatest common divisor of n and m is a 1. So they're co-prime. And then I'm going to pick a constant between 0 and 1, or minus 1 and 0, depending on the sign of n. So it just has to have the same sign as n. Okay. And then from this data, we get another orbifold. So we sort of associate the bundle with respect to the S1 orbit bundle like this. And we have sort of a new sum of branch divisors here. So we have whatever was on the base and then some extra stuff here and here. So delta M is a branch divisor consisting of the 0 and infinity sections of this bundle here. And this just looks like a regular projective bundle built from some line bundle. I'll show in a moment what that is about, maybe right now. It's so that it's an orbi-line bundle whose first Chern class is this integer n times this primitive orbifold class. Okay? So like that. And in sort of a more abstract picture, and this is also from Boyer and Galicki's book, we can think of this commutative diagram where we have a good old sort of projective bundle down here. But artificially, we're sort of thinking of these as orbifolds, but just with the empty set as the orbifold part. And then we have these vertical maps that are set theoretically just the identity, right? But they're actually non-trivial Galois coverings with trivial Galois group. So this is sort of the more abstract picture of what's going on. So we kind of have two bundles here, the sort of the naive bundle and then the orbifold bundle. Okay. All right, so what about those orbifolds? Well, so the thing is, this generalized Calabi construction allows us to construct explicit orbifold Kähler metrics, all those, that each are determined by smooth functions. So you pick a smooth function over some preset interval, so always work with this interval, satisfying certain boundary conditions, okay? So this pick one function, when everything else is fixed, then that determines Kähler metric. And if the base metric from before has constant, oops, there's a misprint, scalar curvature, not constant curvature, scalar curvature, then we call such metrics or classes admissible. The Kähler class and the Kähler metric also depends on that choice of R, because that R was not any part of the orbifold before, but the R goes into the metric. Okay, so what's the point of this? Well, the point of it is that then due to the work of all the many people I mentioned before, one can write up appropriate ODEs that can prescribe Kähler-Einstein or constant scalar curvature, or maybe some other fun geometric condition that you want to put on the metric you're trying to construct. If you want Kähler-Einstein, you actually have to assume that G base is Kähler-Einstein also. And then, of course, there's an ODE on top of that. I want to mention that this idea of having the base also have some mild orbifold singularity also appears in Evelyn Lechandre's Calabi toric metrics in her paper from, I think, 2010 or so. And also some recent joint work I noticed by Apostolov, Calabi, and Godeshan and Lechandre They have a paper entitled Levi-Caylor reductions of CR structures, and there are also examples of such metrics showing up, or orbifolds showing up. All right, so now I want to bring in the S3 join construction into this. And the history here is that this was developed in general by Boyer, Galecki, and Ornia. And we can think of it as the analog of Caylor products. So here is the ingredients in this. So we take a compact quasi-regular Sasaki manifold M over a Caylor orbifold. And we pick it so that the Chern class is a primitive orbifold Caylor class. And then likewise, we take the weighted 3-sphere as a Sasaki structure, and we also pick it so that the class on the base is primitive orbifold. So for example, you want to maybe take the class of the standard Fubini-Studi metric, divide by the order of your CP1W. Then within that class, there is there's sort of a standard extremal Caylor metric that one can use. Okay. And for convenience, I'll let W infinity be less than W0. That doesn't matter. And then I take a certain linear combination of the read vector fields for these two Sasaki structures. So I have to pick some relative prime positive integers, L0 and L infinity. And then the join construction is that we take the product of those two Sasaki structures. That's of course not a Sasaki structure, but then we take the quotient by this action of L. So here's the diagram. Let's just take the product, then you mod out. This is the new Sasaki structure, and that then sits as a S1 orbibundle over the product of the two orbifold quotients that you had of the two original Sasaki structures. Okay, like this. All right, so pi2 is just the product of the projections, and yeah, that's it. I just said that, right? So this bundle here, this is sort of the standard Boothby-Wong construction in vibration. Okay, and then the result would be a quasi-regular Sasaki structure for any choice of relatively prime positive integers L0 and L infinity, but you have to ask, well, when will I get a smooth manifold out of this? And that has to do with the orders relative to the choices of the weights of the S3 and then the choices of L infinity and L0. So here's the condition. So they are only smooth. The new manifold is only smooth if we have this condition satisfied. Okay, and this upsilon S, that's the order. That is also the order of the base n of the quotient orbifold of the manifold to the, or the orbifold to the left. Manifold to the left, quotient orbifold to the left. All right, within there, we have a part of the Sasaki cone that we will focus on. There's a two-dimensional subcone in there that's basically inherited from the Sasaki cone on S3. So we ignore whatever comes from M. And we are interested, as I said in the beginning, in the quasi-regular ones of those. So we look at this lattice within our subcone, W cone. And we can, I don't know, parameterize is the right word, but anyways, array in there, in that part of the Sasaki cone is determined by a pair of relative prime positive integers, V0 and V infinity. And of course, it's not an accident that I'm recycling these letters from before, from the Calabi construction. Okay, so now a lot of what I've said maybe seems, if you've seen me talk before, seems maybe dated, because in fact in 2015-16 we had a paper where we worked with an M as part of this join that was assumed to be regular. Okay, but the new thing is that now we are just assuming it to be quasi-regular. So we needed to reproduce some results in a more general setting. So, you know, there's a good ending to the story because we got the things to be reproduced, but it just, you know, maybe feels a little déjà vu-like. But I promise you that there's some non-trivial nitty-gritty work behind that. And then at the end of the day, we could figure out what happens if we take one of those Sasaki structures, quasi-regular Sasaki structures, and we look at the quotient. What is the Kähler quotient? So here it is. So the bottom line is we get exactly the type of orbifold that I had before out of the Calabi construction. And the way to realign the various data pieces is that the n from before is equal to this, and m is equal to this, and s is an annoying necessary thing that we have to have, the greatest common divisor of L infinity and this. Of course, one way to get out of that is to always choose L infinity to be 1, but we don't necessarily want to do that. And we'll see later that we don't always have the freedom to do that. Okay, and also just makes me feel good. It actually pops out like that. So everything is kind of set up well. And the last missing piece of the story is that we can carefully figure out what the orbifold Kähler forms class is. And if we rescale it, so take a, you know, simply connect a cover of whatever Sasaki structure we have, so that it's primitive, here it is. Here's what it is. So it's this rescale times the class of omega, where omega was the admissible Kähler class from before, when R, and R has to be equal to this. Okay? So that means if we take a quotient by our ray or our Sasaki structure in the ray, we land on one of those things that we can do generalized Calabi construction of metrics within, in up to isotropy. And we know how to get, like we know, you know, the translation, we have the dictionary from one to the other. And then also, because I am going to get to this iteration, the order of this new quasi-regular Sasakian structure can be calculated from the order that we had before the following way. So it's m, v0, v infinity, and the order of n. Okay. All right, and then if we say that we started with n, delta n being a positive Kähler-Einstein metric with Fano index in, then if we pick the L0 and L infinity this way, okay, that would ensure that the first Chern class of the contact bundle vanishes. So there's hope for a Sasaki-Einstein solution. We can start by calculating the first orbifold Chern class of our quotient. And it happens to also be an admissible class. So that's good, right? Otherwise, this setup wouldn't help us at all. And to abuse terms a little bit, we can say the Fano index, because if this is primitive, is this part here. Okay. All right, and then we go back to this admissible construction and the idea of these Kähler-Einstein ODEs. Okay, and we use them to find eta-Einstein up to isotopy, because that is about getting Kähler-Einstein on the transfers, right? And then we will have a quasi-regular Sasaki-Einstein structure somewhere in the array, if and only if. So, you know, this is not enough of this. This is not enough. It's necessary, but we need this equation to be solved, where B and T, they're just practical things I threw in to make it look nicer. Okay. All right. So now we could say, all right, could solve it. And in fact, it's like, you know, old TV shows when you cook. You'd already done part of the preparation, and I haven't, but others have. So Gauntlet, Martelli, Sparks, and Waldron, they actually found all the smooth solutions of this joint, Sasaki-Einsteins. So they have, in their papers, they have prescriptions on how to get them all and how to get the quasi-regular ones if you want. They have one parameter families of those. So our idea was to say, well, let's start then with one of those. So start with a quasi-regular Sasaki-Einstein metric of theirs. So this is their notation, this YPQ. And then iterate, so in a non-trivial way, right? Because I don't want to take the join with S3 just because then that's just making product metrics a higher and higher dimension. And then try and do it again and again. And it's sort of like this process, right, where you have to solve the equation from before, this equation that had the integral in it. And then at every stage, you pick your L0, your L infinity, W0, and W infinity. And then you could somehow create a non-trivial stairway to something like some high dimensional examples. That's the sort of the idea. But if you want smooth examples, then every time you take a step, you have to make sure that this condition is satisfied. So you have to calculate the order. So we know how to calculate the order, but then you have to feed it in, you know, and make sure that these two things are co-prime, and then do it again, do it again. And I mean, it's enticing because there seems to be a lot of choices, right? We can choose our W's as we want. So it seems like this should be possible. Just to sort of introduce some notation and language to wrap our heads around this, we can think of S3 as, with the round Sasaki-Einstein metric, so just the standard metric of S3, as a stage 1 join. And I'm calling it stage 1 join because its quotient is CP1, but that could also be named stage 1 so-called dot manifold. And in a moment, I'm going to say briefly what I mean by that. And then at the YPQ, that would be stage 3. Okay, and that's quotient could be viewed as a stage 2, but orbifold. And then here's an example where we take one more step to stage 3. Okay, one more non-trivial step. So here it is. So what you see here is a YPQ with a choice of P and a choice of Q that depends on a parameter T. And then we take a join where L0 and L infinity also depend on T, and W1, W0 and W infinity, they're just, for whatever reason, 17 and 3. That has a smooth quasi-regular Sasaki-Einstein structure. And the quasi-regular quotient is a stage 3 bot orbifold. And it's given by log pair again. So this is, you can think of this as a manifold with this extra orbifold structure on top. Here is the sum of the branch divisors with ramification indices. And here's the prescription. And I'll explain in a moment what A, B, and C mean. just see that they're very complicated expressions in T. And here are the M's. The first pair of M's are fine, a third are fine. These depend on T, right? So these are the ramification indices that goes up here, okay? So let's just let that stand a little bit, okay? So, and I mean, so what I want to say is like, in the paper by the 4 people I mentioned before, Gordon, Martelli, Sparks, and Waldron, they give, you know, prescriptions for 1 parameter families of P's and Q's that gives us, you know, smooth quasi-regular Sasaki-Einstein ones. So we fed those into it. Then we took the join, but then we went back and said, now we want this stage 3 to be smooth as well. So we fiddled with their parameter and assumed more about the parameter. So it's still a 1 parameter group, but it's a little more involved. All right, so what are these Bott manifolds? So they were first, and I've been told I pronounce this in a bad way, but I do what I can. So first introduced by Grossberg and Kirschon. And I got to know about those doing a joint work with Boyan Calderbank, where we studied the smooth cases from the point of view of Kähler geometry and looking for special Kähler metrics. And the way we can think of them is that we have some Bott towers where we can say stage 1 would be CP1. Stage 0 is really just a point. Stage 2 is here's a book surface. So you pick a line bundle on CP1, you add the trivial bundle, you projectivize, you get a CP1 bundle over this stage 1 one. Then you do it again, but now you have to pick a line bundle over the total space of this one. And that can be determined by choosing 2 integers, B and C. And then you have a new CP1 bundle over the previous stage manifold. Okay. And you can keep doing that again and again and again. And if you go beyond stage 3, you would want to use a different notation than this, maybe introduce some matrices, which indeed people do. So and so on. All right. So what happened with the orbifold thing is that these devices that were up in the description before, they're just natural exceptional devices that come from the 0 and an infinity section at every stage you take. So you have, because you have these bundles that have these sections. So you can add this orbifold structure in a natural way. Oops, like that. So that's all I'm going to say about that. It's a huge story about these manifolds, but I just wanted to at least mention them. Maybe just a little bit more. A natural question would be to ask, do all the stage 3 Bott orbifolds arise doing these iterated joints? And the answer is no. So nope, because in that key proposition that I had with Charles, these line bundles that we get at every stage from the quotient, they have to have a sign. So their Chern class is like has a sign. So you can easily think of cases where that wouldn't be the case. So for example, the Koizes-Akane manifold. So this is actually a stage 3 where the first choice is you take the trivial line bundle. And then the second choice, you pull back degree 1 and degree -1 line bundles for each of the pieces of your product, right? So this line bundle here, that definitely does not have a sign, right? The Chern class of that one is not plus minus a Kähler class. So that one would not come up that way. But it does, you know, just sort of a by the way, we can have it appear as part of the Sasaki story. So recently, Charles and I saw that it turns out that it's a regular quotient of a so-called Yamasaki fiber join, which is a different construction. It's not the join I'm talking about here. Sadly, the corresponding Sasaki structure that it pops up as is not the Sasaki-Einstein. It's one of the CSCs. There are many of those on this manifold, and it's one of those. So, but that's a different story. And again, I want to say this is joined with Charles Boyer. All right, so iterated join. I took one iteration, right? That's all I did. But we could keep going. So we could keep going. It's like a real sort of tiresome and messy, but also a little bit fun thing to do, because you have to sort of do a little bit of baby number theory, right? Show things are co-prime and so on and so forth. And so we managed to persevere a little bit more and show that in dimension 9 and 11, we can build on the example I had before and get counterful infinite families of quasi-regular smooth Sasaki-Einstein structures. And they are non-trivial, I should say. We're not cheating by taking a product at any stage, so they're every time we do something non-trivial. So the conjecture would be that you can always, pick a dimension and you can reach it. That's not quite a proof that they're infinite dimensional, but that's the conjecture, that you can keep going and you can get smooth Sasaki-Einstein structures in all odd dimensions with 0 trivial iterations. But we haven't proven that. It's very easy to get around the smoothness condition and find an algorithm that you can then show will never break down. Even the example I showed before, it was a lot of sitting with pen and paper and making a good guess for choices of data to fit in. So, it's would be nice if someone could show it. But I don't think it's just an easy induction at all. I think it's a little complicated. Maybe another way to do it is to, one can interpret this in the toric setting, because if you start with a CP1 or you start with the YPQs, it's definitely toric what we're doing. So, all right. Okay, so I mentioned several people's names here, but just to keep it to one page, I'm just going to mention the stuff that, except for the book, the Boyer and Galigi's book, I'm just going to mention the things I've been involved with that all are all part of this talk. So the admissible construction, the paper Apostolo, Calabi, and Godeshan has a lot about what these metrics actually look like, and it would be easy enough to then imagine that with orbifolds. Also, the paper with Boyer and I from 2016 that does the case where M is regular has a lot of background. For the bot manifolds, the joint paper with Calabi and Boyer also has a lot of references to the rest of the literature about these manifolds. And then for the iteration, Charles and I have a recently published paper in Journal of Geometry and Physics. And then we have 2 preprints. This one here is the one that takes care of that key proposition. And then this one is a shorter paper that was meant, it was meant for it actually is still meant for the conference in Toulouse, has been postponed for now. And then by the way, the thing about Yamasaki joints, that is something we have written on lately in this preprint that we posted. So that is all I had to say. So thank you very much for staying with me.
Thank you very much, Christina. So let's thank the speaker first of all. And I have some questions. One question is about what is happening in the constant scalar cage about this conjecture. So do you have an equivalent of it, and did you do some progress on that? In the case it's not Einstein, of course.
So yeah, so you're absolutely right. So I chose to only focus on the Sasaki-Einstein, but you can make a similar conjecture for constant, and in some sense it would be more likely to be true, right? I mean, it's easier to solve.
It should be
problem
easier, so yeah.
It's almost maybe too easy because you have no idea. Like you're trying to build this staircase, right, to heaven, but now you have too many choices of which direction to go, right? And so to try to find out which one will work and which one will keep working. I've been noodling with it, and Charles has been noodling with it, but we haven't, we have a bunch of examples and stuff like that, but haven't been able to see that you can keep going. So that would still be a conjecture.
So, okay, you don't know. Are there questions, comments? I imagine Vetislav may ask.
Yeah, I have a question. I'm confused, actually. I don't understand your conjecture. So what exactly this conjecture says? Can you repeat for me, please?
Okay. So every time, so if we take a joint, right?
Okay.
And we find a quasi-regular Sasaki-Einstein structure on it, right?
Okay. Yes.
Then we could take that one and take another join with that. So that plays the role of M now.
So you're joining again with S1? Or
yes, yeah, so you keep joining with S3.
Okay, okay.
And of course, if you choose W to be 1, 1, then all you're doing is you're just taking a direct. You're just taking a product right down on the Kähler level. So I'm saying, don't do that, right? So you're not allowed to do that. So you always have to be, at least one of the W's has to not be 1.
Okay, I understand the conjecture now. So my question is the following. So to me, in this whole theory, there is a Yau-Tian-Donaldson conjectures, which says that existence is subjected to some stability condition.
Mm-hmm.
So is that conjecture is saying essentially that they will be automatically stable? Is that what you want to say?
Well, I mean, I guess
in the Tori case, of course, but I guess your conjecture is a little bit more general, right?
Yeah, and it's also just saying there are some, right? There are also some where they're not, right? Like it's just, this is just a sort of a conjecture saying existence in higher dimensions of some.
Yeah, but let me put it another way. So you don't have any issues with positivity of these polynomials that you find from the ODE?
No, I don't think that's going to be the problem. Not for the
well, I believe the stability is precisely the positivity. And when you, by the way, when you talk about constant scalar curvature, this is this may be a Ginian problem.
Oh no, yeah, constant scalar. I 100% agree with constant scalar curvature. Absolutely, 100%.
So what do you think here in this setting that you don't expect any problems with stability? It will be like in the Tori case.
Yeah, so I hear what you're saying about the polynomial. I think because the way the joint construction is, we are in such a narrow lane of the admissible construction, just with the choices, that I do think that the extremal polynomial that's sort of lurking there, I think it's automatically positive if you can solve it.
Mm-hmm.
I'd have to check, but I think so.
Yeah, this is like in the Koisu-Sakane type. That we actually wrote many years ago.
Yeah, exactly. So I don't think that's an issue here.
So it may be that another way to formulate your conjecture is to say that in this particular construction you always have stability, because now we know that the existence of Sasaki-Einstein is equivalent with
Yeah, that's right.
Can I make a remark? Hello?
Yeah.
Yeah. Okay. So, yeah, Vesti, I think so. We can prove that we always get solutions if you just allowed the Sasakian objects to be orbifolds. So if you let them to be orbifolds, then on that Kähler cone that's over there, where you're actually measuring the stability, then you have something with the non-isolated singularity. So whatever you kind of have to deal with that, I think, in order to bring in the stability arguments. But I mean, we certainly believe that it's true. I mean, here it was just done nitty gritty, as Christina said. You can find, and the fact that you can find up to 11 countably infinitely many families, I mean, it seems pretty clear to us, I guess, that the conjecture is true. But I mean, the way to do it with stability, I think, means dealing with non-isolated singularities in that Kähler cone.
Well,
So you would get Ricci flat examples, but they would be, I mean, so I don't know how much stability has been studied in that setting.
You can alternatively do with a quasi-regular quotient, which is an orbifold, and in that context,
Oh yeah, yeah.
that is quite clear.
Yeah, but the quasi-regular quotient is, yeah, I mean.
You can do actually any quasi-regular quotient, whichever you want, and then do the slightly weighted version of stability on that.
Yeah. Yeah, but doesn't it boil down to, I mean, even the formulation of stability is usually done on that cone. Because
yes. Yeah, well, you have to work something out. Yeah, I agree.
Yeah, that's right. Yeah.
Yeah. Worth looking at for sure.
Are there any other questions or remarks?
Maybe I just make one more remark that Christina didn't mention there, because I guess lack of time, that we have results on topologically what these manifolds look like. In dimension 7, for example, they have the rational cohomology of the twofold connected sum of S2 cross S3, and then they have torsion in H4, which these integers like V0 and V infinity, they contribute to the torsion in H upper 4. So we do have some topology, but the thing gets much more complicated, obviously, as you go up in dimension.
Yeah.
Okay, thank you. Thank you very much, Christina. Thank you very much for this nice talk.
Thank you.
So let's thank Christina, as we should now.